In this video, we're going to generate some qualitative MO diagrams of some simple polyatomic molecules. We're going to be using the same principles that we used when we generated MO diagrams for our hetero and homonuclear diatomics. That is, we're going to be combining AOs with symmetry-related orbitals. And as a reminder, in order for these orbitals to combine, the orbitals must be of similar energy. A major difference is going to be that we're not going to be combining together atomic orbitals with other atomic orbitals, but we're going to be combining together atomic orbitals plus something called Ligand group orbitals. Ligand group orbitals are simply atomic orbital combinations resulting from the atomic orbitals of the atoms surrounding a central atom of the molecule. These are also referred to as SALCs. Or symmetry-adapted linear combinations. These are generated using group theoretical methods, and a subsequent video will go into exactly how these are generated. For now, we're just going to utilize SALCs that we've looked up in tables that have contained pre-generated SALCs in given symmetries. As we go through, I'm going to use the term ligand group orbitals and SALCs interchangeably. When I refer to one versus the other, I'm really meaning the same thing. We're going to start by generating the molecular orbital diagram for water. So water is contained in C2V symmetry. And a way in which we can think about water is that we've taken a dihydrogen, we've elongated that HH bond, and we've added an oxygen atom to the center of that HH bond. So what we're going to do is we're going to generate ligand group orbitals from our hydrogen 1s atomic orbitals. And these ligand group orbitals are going to look very similar to what the molecular orbitals of H2 looked like. So, just very quickly, the molecular orbital diagram from H2 is generated from a 1s and a 1s combination from the two hydrogen atoms, forming a bonding and an antibonding orbital. This is in d infinity h symmetry, so this is a sigma g, and this is a sigma u orbital. This orbital looks like this, and the sigma u looks like that. As we go through and we elongate that HH bond, because those two 1s orbitals are further apart, there's going to be less overlap, but we can still form linear combinations of those hydrogen 1s orbitals. You're still going to get one that's going to go up and one that's going to go down. The one that goes lower in energy corresponds to your bonding combination in H2, but it now looks like that. It looks more like two isolated hydrogen 1s orbitals. And the antibonding combination looks the same, but those are now out of phase. Now, these are no longer in D infinity H symmetry. We're talking about two hydrogens that are in water, and water is in the C2V point group. So our symmetry labels have to match that for C2V. I'm going to quickly write out the character table for the C2V point group. We have this. Looking through, this lower energy bonding combination has the same symmetry as the A1 representation. It's symmetric with respect to E, the C2 axis, the sigma V, and the sigma V prime. Because of that, we give this one an A1 label. If we look at this antibonding combination, we're symmetric with respect to E. You do that C2 rotation, and this lobe comes over here. This one goes there, so it interconverts. It's anti-symmetric. If we look at the sigma V, which is defined along the XZ plane, our y-axis goes that way as we defined it. It is anti-symmetric, but it's symmetric with respect to the YZ plane. Therefore, this gets a B2 symmetry label. These are now going to combine with the symmetry-related atomic orbitals on that central oxygen atom. So going through, we're going to draw our energy axis. Over here, we're going to put our oxygen atom atomic orbitals. So you have your 2s, which has A1 symmetry, the 2pz, which has A1 symmetry, 2px, B1, and 2py, B2 symmetry. Over here, we're going to put our HH SALCs. So you have your A1, that bonding type SALC, and the B2. And we're going to just overlap our SALCs with our atomic orbitals from the oxygen. Going through and doing this, because that oxygen 2s orbital is buried low in energy relative to the 2p orbitals on oxygen and the hydrogen SALCs, we're going to bring this over and to a first approximation just say that that is non-bonding. And it's going to remain A1 symmetry. We're going to overlap our PZ with the A1 orbital, forming a bonding and an anti-bonding combination. We're going to overlap the B2, forming a bonding and an anti-bonding combination. And that B1 is going to come across as being a non-bonding orbital. To distinguish these various orbitals, we're going to give these symmetry labels indices, starting with 1, 2, and 3 for our A1s, 1 and 2 for our B2s, and 1 for that B1. Filling in electrons, we have 6 electrons from oxygen plus 2 from our 2 hydrogens for a total of 8. So we get this. with this B1 being our highest occupied molecular orbital, and this B2 star being the lowest unoccupied molecular orbital. We're now going to sketch what our molecular orbitals look like. So the 1A1, that's essentially a non-bonding oxygen 2s, so it's just 2s, and so it doesn't look like a 2s orbital. I'm just going to put 2 lines there to denote that you have the hydrogen nuclei there. The 2A1 was a combination of this SALC from the hydrogens plus the oxygen 2pz. So what it's going to look like is this, with this lobe here on the 2pz overlapping with that in-phase SALC combination. The 1B2 is going to be the out-of-phase SALC combination plus the 2py, and when you overlap these, it's going to look something like this. Because we have this in-phase lobe overlapping with this in-phase, this out-of-phase overlapping with this out-of-phase. The 1B1, to a first approximation, is a non-bonding 2px orbital. I'm going to reorient the water molecule like this so that I can draw it like that. The out-of-phase combinations, the 2B2 star, are now this out-of-phase with this combination. So when you go through and draw out what that molecular orbital looks like, it's going to look like that. And your A1 star is going to be this combination here, out of phase with your 2pz. So it is going to look like this. As we did with our diatomics, we can make analogies between the MO diagram for water and its Lewis structure. So the Lewis structure says that water has 2 lone pairs. According to the MO diagram, one is from this 1A1 2s orbital, and the other one results from your highest occupied molecular orbital, that 1B1 orbital. Furthermore, we have 2 molecular orbitals that have significant hydrogen-oxygen bonding. It's your 1B2 and your 2A1, which correspond nominally to those bonding type orbitals. Although, as I said before, you don't want to get too carried away with making analogies between the Lewis structure and the MO diagram. Now, to go back and quickly review what we just did, the first thing that we did is we identified the molecular point group. We then generated our ligand group orbitals for the ligand atomic orbitals, and then 3, we combine the ligand group orbitals with symmetry and energy-related atomic orbitals of the central atom. What we're going to do now is we're going to tackle a slightly more complicated molecule using this method and generate its molecular orbital diagram. Ammonia. So ammonia is in C3V symmetry. Just reorienting this. We have it like this. And what we're going to do is we're going to generate Ligand group orbitals of the hydrogen 1s orbitals. So the Ligand group orbitals for those hydrogen 1s's those split into an A1 type orbital, where those are all in phase, and a degenerate E-type orbital. That looks like that. Drawing out our molecular orbital diagram. I'm going to put nitrogen here, and then the H3 SALCs over here. You have your 2p orbitals. The pz transforms as an A1 orbital, and the 2px, 2py transforms as a degenerate E set. And you have your 2s orbital, which also has A1 symmetry. Over here for the hydrogens, you have your E and your A1. The A1 is going to combine here. Like that. Remember, nitrogen, the 2s orbital, isn't buried so deeply in energy, so it can energetically participate in bonding. But the consequence of this is that you can also get mixing of the pz orbital into that. Forming that. You also have your E-type orbitals. That can overlap like that. So you have your 1A1, your 1E, your 2A1, your 3A1 star, and your 2E orbitals. Putting electrons in. We arrive at that. So the HOMO is our 2A1, and our LUMO, as we've drawn, is the 3A1 star. We can go through and draw what these various molecular orbitals look like. So the 1A1 is this, plus the nitrogen 2s orbital. So it's going to look like that because you're all in phase, it's overlapping. The 1e, you have one pair. That would be made up of that orbital plus the py. So what this molecular orbital is going to look like is that. Just putting in that line to signify where the nucleus is of the hydrogen atom that has a node there. The other one is this plus the px. So this is going to look like that. So our degenerate 1e orbitals are here, and that 2a1, just reorienting the molecule so that we can emphasize the nodal structure. You have those SALCs plus the PZ, and this results in a molecular orbital that looks something like that. Drawing the Lewis structure of ammonia, there's a lone pair on nitrogen, and that lone pair is chemically active. It's your Lewis basic site. This lone pair corresponds to this 2a1 orbital that results from the hydrogen 1s and the pz. So as we can see, this isn't exclusively a nitrogen-dominated lone pair. There's significant hydrogen character in this molecular orbital. So as we can see, we can use these Lewis structures as a guide. However, the actual underlying bonding of the molecule is actually much more complex than what you would predict from simple Lewis theory. We're going to end this by deriving the MO diagram for trifluorocarbene. So trifluorocarbene has this Lewis structure where we have a lone pair located on the carbon atom, and of course there's the lone pairs on the fluorines, just putting those in for completeness. This is a molecule that is in C2V symmetry. This is a little bit more complicated than the MO diagram that we generated for water because we have to consider the 2p atomic orbitals from fluorine. So we're going to generate Ligand group orbitals for these 2p combinations. And just as we did before, to conceptually see where these Ligand group orbitals are coming from, we're going to start with the FF molecule. We're going to elongate that FF bond. And then we're going to take a carbon atom and we're going to plop it down in the middle there, forming our trifluorocarbene by overlapping the carbon atomic orbitals with the fluorine SALCs, or the fluorine ligand group orbitals. This is the molecular orbital diagram for F2 that we generated before. I have the symmetry labels denoting that D infinity H symmetry. We have the combinations from our deeply buried 2s combinations, and then we have our 2p combinations up higher in energy. These are going to change in energy as we elongate that FF bond. Furthermore, because we have that carbon atom in the center, these orbitals are going to reorient themselves such that the z-axis for the atomic orbital is going to be located along the fluorine-carbon bond. So when we do this and we drop into C2V symmetry, the symmetry labels change. So we now have our 2s combinations and the 2p combinations. As I said, notice that now we have the 2p z orbitals oriented along that carbon-fluorine bond. Adding in the carbon atomic orbitals with their symmetry labels, we're now going to overlap the fluorine SALCs with the carbon atomic orbitals. And we're going to put a break in energy here and also up here higher in energy. So first, these 2s combinations are going to be too low in energy to overlap with the carbon 2s or the 2p's. So we're going to bring these across as essentially non-bonding. So you have that A1 and then that B1 that are being brought across as being non-bonding. And they're going to look very similar to the SALCs that we have here. I'm going to go through and I'm going to label the fluorine-based SALCs with numbers so that we can see where these various combinations are coming from. Okay. So the first thing we're going to do is we're going to overlap the 2p SALC that I have labeled 1 with the carbon 1s or 2s orbital. So that's going to form a bonding combination and is also going to form an antibonding combination. We're going to label this A1 and this one A1 star. We're now going to overlap our B2 combination from up here with a carbon 2p, the 2py. Okay. Next, we're going to overlap this A1 combination with a carbon 2pz orbital. Now this is going to be up higher in energy than it otherwise would be because there's going to be a little bit of mixing also in from that 2s and there. So these A1s can mix together. We're going to get a very high energy A1 star. We're now going to add in this B1 combination with the 2px B1 orbital on the carbon atom. That's going to form a bonding and an antibonding combination. Okay. This A2 type SALC has no combination over here, so it's going to come across as being non-bonding. And finally, we have one leftover B2 SALC. This B2 SALC up here is going to combine in and mix in with this B2, generating a slightly antibonding orbital. So it's going to be like that. I'm going to go ahead and redraw this on the next slide so that it can be cleaned up a little bit. Okay, so here I've redrawn the MOs that result from our overlap between our carbon atomic orbitals and our fluorine ligand group orbitals. What we have are our non-bonding orbitals from the fluorine SALCs there. We have this A1 combination primarily from the carbon 2s and this SALC here, followed by a B2 combination that's coming from this SALC up here, high in energy, SALC number 6, and the carbon 2py. We have this A1 combination primarily from this A1 SALC on the F2 and the 2pz, but there's also significant mixing in from this 2s orbital and this A1 SALC. We have the B1 combination from the px orbital on carbon and this SALC here, B1 SALC from the F2. The non-bonding A2 combination from this out of phase combination on the F2, followed by the antibonding B2 that is dominated by the 2py and a combination of SALC 6 and SALC 5. The 4A1 star antibonding combination resulting from this antibonding combination. The B1 star, which is resulting from this is its bonding pair, and then this B2 star here. This is the B2 bonding combination, and it's resulting from an antibonding 2py in both SALC 6 and SALC 5. And then finally, the very high energy 5A1 star. The two fluorine atoms are going to come with 14 electrons. The carbon atom is going to come with 4 electrons for a total of 18 electrons. So just going through and filling these in. We arrive at this with our 4A1 as the highest occupied molecular orbital and the 2B1 star as the lowest unoccupied molecular orbital. I'm going to finish by plotting out what these molecular orbitals look like as generated from an electronic structure calculation. Plotted here are our ligand group orbitals, or SALCs, for our F2 fragment, along with the molecular orbital energy ordering for the CF2 molecular orbitals that we derived. In addition, I've put down the primary contributions to several of these molecular orbitals based on the atomic orbitals from carbon and the ligand group orbitals overlapping with those. The lowest energy A1 and B2 molecular orbitals look virtually identical to these SALCs over here, so I'm not going to replot those. Instead, I'm going to plot all of these higher energy molecular orbitals so we can see what they look like. Plotted here are the molecular orbitals generated from an electronic structure calculation program for the molecular orbitals of CF2. And what we have are the 2A1 orbital, and you can see how this would result from a 2s orbital on carbon overlapping into that SALC 1. Here we have the 2b2, so this would result from a 2p orbital overlapping into there. This is followed by the 3A1. So this would be from a PZ orbital coming in and overlapping in there. We then have the 1B1 followed by the non-bonding 1A2. So it is just that SALC right there. Up here we get into our antibonding configurations. The 3B1 star, the HOMO, the 4A1 star. So we'll just note that that's the highest occupied molecular orbital. The 2B1 star, which is our LUMO, the 4B2 star here, and then finally this weird looking orbital is the 5A1 star, which has that shape because of the extensive amount of mixing that's going in making that particular molecular orbital. So as you can see, these results using a reasonably high level calculation yield the same molecular orbitals that we would qualitatively obtain just by doing the simple overlap of the carbon atomic orbitals with our F2 ligand generated orbitals, or SALCs. What I have plotted here are the occupied molecular orbitals of difluorocarbene. And just to remind ourselves, the Lewis structure of difluorocarbene is this. Now, it might be hard to reconcile the localized electron pair domains in the Lewis structure of difluorocarbene with the delocalized molecular orbital description. But remember, both the molecular orbital diagram and the Lewis structure are different representations of the difluorocarbene molecule, and both actually coincide nicely with the chemistry observed of difluorocarbene and carbenes in general. In sophomore organic chemistry, you rationalize a lot of the chemistry of carbenes by considering this carbon-base lone pair and how it would react with other compounds. The molecular orbital diagram shows that the highest occupied molecular orbital is centered almost exclusively on that carbon atom with that large amount of density pointed out in the same direction that you get with the Lewis structure, pointing out from the carbene molecule. So in this sense, the two views coincide very nicely. We can rationalize the same chemistries using a molecular orbital diagram that we could rationalize from a simple Lewis structure. In fact, other aspects of the Lewis structure versus the molecular orbital diagram aren't necessarily incompatible. We can do mathematical transformations on these molecular orbitals, which will localize the electrons within the molecule. The resulting localized molecular orbitals coincide very nicely with what you would predict using a valence bond theory calculation, which in turn coincides nicely with the Lewis structure. So all of these different representations converge to give you the same idea of the structure of these molecules and how they react. In a subsequent video, we're going to generate molecular orbital diagrams using fragment molecular orbitals, applying these principles that we've learned in the previous two videos to generating more complex molecular orbital diagrams.